Nice. So, welcome back. Well, we're already at our final talk of the day here, main track land. Yee. So, our next two speakers, they're not a stranger to the community. And Ramon, can you tell our audience a bit about them?
Absolutely. So here we go, folks. Our next speaker comes in two. So we've got Kir, who is a platform engineer at Shopify, quite the culinary expert. He enjoys cooking and touring his favorite places to eat, and I hear writing up about them. And Julik is a software developer at WeTransfer. He gave a lightning talk at Euroco last year, and he plays the trumpet. A musician. Let's hope that he makes an appearance at karaoke today. But I'll let him toot his own horn. Well, folks, let's hear a little bit about sleeping on the job.
Hello, everyone. Welcome to this talk about background jobs. My name is Julik, and today with me we have a wonderful Mr. Kir. And we thought that it's really worth it to talk about background jobs because these background jobs are also a best way to crash your application. So they're not only very useful, but they can also be dangerous. Why they can be dangerous is because they run with a delay, which means that they do not start executing immediately when you spool them up. They run for a certain amount of time, which is not always predictable. So, for example, it is possible that you spool up a certain job and you expect it to complete within, say, 300 milliseconds or half a second or a second, but instead it takes 10 seconds or a minute. There are many of the background jobs running at the same time. Even if you're running a single Sidekiq worker, you're going to be running multiple flows of execution simultaneously. And some of those jobs take a longer time than others to complete or to fail, meaning that it's a little bit difficult at times to predict how long an execution of a certain task in your application can take. And we think this session can be useful to you even if you're not necessarily a company running a very large application, because knowing how to approach background jobs safely will potentially allow you to size your service better. That is to figure out how many servers you need to run for your background jobs. But also, it could give you some indications and some hints on where to start looking if you feel that your background jobs cluster or your background jobs code is doing something silly or something that you do not necessarily want it to be doing. This is a touchy topic. Why? Because doing things with background jobs well is controlling parallel processing in time, and sometimes you have to control it in a way which is not immediate. This image here, for those who never seen it before, this is a control panel of the Chernobyl-like RBMK nuclear reactor. And the control panel on the right actually allows you to manually control the load or control the control rods within the separate nuclear reactor channels. And it was actually the job of the nuclear reactor operator on every shift to ensure that these channels heat up and produce power evenly. And it required a lot of manual input. And to provide this input, what you would actually do here is you would hold one of these colored buttons on the right, and then you would operate this rocker switch on the left to move the control rods up or down. And it was actually known to be a stressful job for the nuclear reactor operators, because those RBMK reactors require this babysitting continuously to make sure that in time and over time, their power production within those reactor channels would stay even. And this theme of having your background job executions even or similar in terms of duration and load they cause on your system, we're going to touch that multiple times in this presentation. And the first thing that we're going to need is to have a way to visualize background jobs. And what we are suggesting is this kind of a timeline swim lane view, where you look at your flows of execution from left to right, and we have time laid out from left to right. And your little job, which is, say, a job of a green class, in this case, it gets added to your message queue, which happens when you call, process payment process payment job.perform later, then your job gets spooled into the queue. Then it spends some time in the queue, and then it gets picked up by one of the worker threads or worker processes for execution. And then it takes some time to execute, and then it completes. And then there is a different job which gets picked up by the same worker thread, which then also gets executed, et cetera, et cetera, et cetera. And you have multiple workers and threads of execution running at the same time, and each one of them is independently executing some kind of a job. I think this is important because to know what to do with your system, you need a basic degree of knowing what your system is doing, which brings us to this.
Thanks, Julik. You still have that picture in mind of that huge control plane from a nuclear reactor, where you can imagine workers watching all the metrics and levels and figuring out what to do. And we want to have the same level of observability into the live production system, and to know what's happening with the background jobs. Are they stuck? Are they running? At what rate they're executing? So it's important to have observability into our system. Next slide. There is all sorts of metrics that we want to see of our background jobs. It's the throughput, the rate of the jobs in time per minute or per second, the performance, how long does each job by class takes, and distribution, usually P99, P95, P50, and so on, to see what is the distribution of performance of different job classes. At Shopify, we use Datadog. It's a third-party vendor that gives you monitoring. Because we use that because we prefer to build the actual e-commerce and infrastructure for e-commerce for ourselves. But other stuff like monitoring, we use third-party tools. In this case, Datadog.
But come on. I mean, at what cost? What's the charge in Datadog per single metric that you want to save? That's really extreme. We roll more frugally at WeTransfer, and what we do, we use AppSignal, which is our provider for application performance monitoring. And with them, creating extra metrics is pretty easy, and it doesn't cost extra. So that's what we use. And an example of a dashboard that you could use for something like this is what we have here. So on the bottom, we see the number of jobs that our workers have received for execution from our web application. And on the top, we see the jobs which are currently executing. So if we would be seeing very large spikes here on the top, then we would suspect that there was a very large spike in a certain type of job. And here we can observe the general pattern in how many jobs are dominating the cluster at this specific moment. And here, for example, we are at 10 o'clock at night. And right now, the deletions start executing. So here we see the scrub prefix and the scrub transfer jobs, which start executing at night when we expire our old data. But whichever tool you use, I would say that these are the metrics that you need, because you need to be able to find the jobs which are the outliers. So the jobs which take a lot more time than others, or the jobs that stall for whatever reason, or the jobs that fail a lot. Another thing that you need to take into account is the two-step deploy. And with the two-step deploy, I mean this. So normally you deploy in just 2 steps here with a blue-green release. So you add a process payment job. You have committed your changes. They are in master. You are deploying your version, and then it's running. And then your application spools the process payment job and executes the process payment job. Easy, right? Well, most likely you're going to run into a situation like this. And what's going to happen is that your background worker server is still running your old version of the application, which you have already introduced your spooling of your new job class in your web application server, which means that within this period of time, this yellow window, your web application server is going to spool the job, and your old worker is going to pick up this job from the job queue, and it's going to try to instantiate the process payment job, and it's not going to be able to. And so you're going to get an error. So the answer to this is to actually deploy in 2 steps. So instead of doing a blue-green, you do a blue-red-green. And so in the first version that you deploy, you make the job code itself available so that every worker can find the job class to execute the job. And only once you know that all of your background workers are running the newer version of the code, which has this job, then you deploy your version, which starts actually enqueuing the job. It's a simple thing, not very hard to ensure that it happens, but it can be very useful. So deploy in 2 steps. And if you have a smaller application or you want to cheat a little bit, you can solve this a bit simpler, and you can actually deploy in sequence, meaning you deploy your background workers first, you ensure that they all have replaced with the new version, and then you deploy your web application. And at WeTransfer, we really pay attention to this. And so we do this as part of a code review. So we just say, yeah, this change is good to go, but we're putting it in request changes so that it can be broken up into pull requests, which the first pull request adds the requisite job code, and the second pull request, which comes after and will be deployed afterwards, adds the spooling of the job. What do you think?
Come on, we're all humans. We cannot spot all the things in every PR, and I'm sure as a reviewer, I would often miss noticing all the stuff like this. So I wouldn't actually rely on people here. At Shopify, we use GitHub bots to detect different changes, different patterns on your PR. And this is an example of a comment by a bot on a PR that introduced a new job class. It suggests the author of the PR to read some documentation and to make sure that they're doing this 2-step deploy process that you discussed, Julik.
Oh, you fancy people. You will pass me the source code of this caution table once we're finished recording, okay? Let's move to the next one. So there is also this thing. Where do you store your jobs, right, Kir?
Right. It's important to talk. We're talking about these concepts and best practices in working with background jobs, but I think it's important to also touch on the storage and how that storage scales and what makes it durable. At Shopify, we've been using Redis for probably a decade now. We have some really good operational experience with it. And we used to run it in the data center when we were at the data center. Now we're in cloud. We run Redis in cloud. In GCP, when it's time to move for us from one cloud to another, we will still be able to use Redis that we manage ourselves there. Which is why we invest into our Redis stack. We run highly available Redis with 2 instances, one being primary, and the watcher process that switches one follower to the primary if the previous primary is not working well anymore. And that's managed through DNS. And to store jobs reliably in Redis, we use lpop lpush, which moves a job from a queue into the worker queue. And the worker queue would get acknowledged if the job is done processing, or if the job worker has died, it would not get acknowledged, and it would get back into the queue eventually. Next slide, please. It's important to note that Redis as a database is a single CPU. It's not concurrent, and eventually you would run out of that single CPU on Redis. So you got to figure out how you horizontally scale Redis. Of course, you can make your client, your Rails app, your Ruby app, to connect to multiple Redises and choose to which Redis to connect, and so on. But that logic becomes really complex. Instead, we run Envoy proxy, which for the client looks like just one single Redis. But underneath, Redis proxy speaks Redis protocol and forwards commands to different Redises depending on the key prefix or the hash of the key, which allows us to invisibly add more capacity into our Redis cluster without having to change a single line of the client code. So that's how we run Redis, and that's how we use Redis for background jobs. And I'm curious to learn how you approach that at WeTransfer, Julik.
Well, we took something off the shelf. So we use AWS. We're not on GCP, and we've decided to go for the solution called SQS, which is something that AWS provides. And SQS is a message queue service, and it's a managed thing. It has built-in durability, meaning that your jobs are not going to disappear. They have very good durability guarantees. They have a number of really nice integrations with other AWS services, such as S3 notifications. And also, one of the great advantages of SQS is that it is not sophisticated. It is managed, and it's not sophisticated. So we really like it for the things it does not have. For example, it does not allow you to prioritize jobs. It does not have topics or sub-queues, so you cannot create complex topologies of the separate queues that you fetch from. You create one queue. It takes a long time, but then there is just this one queue that you have. There is no exactly once received, so there is no complex protocol. When you pull something from SQS, you basically open a long polling HTTP request, and it just feeds you jobs to perform. And the only setting is a URL that you connect to as your endpoint for sending jobs and for listening for the new messages to execute. And you have to delete the job manually from SQS. And all of our services use SQS through a library called Skewer, which we wrote ourselves, and which also includes an active job integration. So our Rails app uses Skewer through active jobs and talks to SQS through Skewer. And our smaller services, they work with Skewer directly. Skewer you can find here on GitHub.
I guess you're just vendor locked to AWS, but with SQS. But
yeah, man. I mean, we just do not have time to contemplate, moving from one cloud platform to another every 6 months or so. It's choices everywhere. The next thing that we need to cover is something that's called sequential execution, which is not something you are very likely to bump into when you have very, very few of something. But it is surprisingly easy to start getting very, very many of something in your application if not having many of something is not one of your priorities. For example, imagine you add a notifications table, and every now and then things need to be deleted from that notifications table because daily you might be generating a few thousand notifications, for example. And usually you do this in jobs which perform things in large batches, and this can create an interesting situation. If we look at it in terms of our time swim lane view or timeline view, and we imagine that this blue job suddenly takes a really, really long time because it's processing a ton of items, what happens there is that it entirely takes over a thread of execution. So one of your workers or threads is taken out of rotation, and it's occupied by this one very long-running job. And this is not a pattern that you want to create, because with 3 worker threads, for instance, it is enough to have 3 of those blue jobs to take all of your capacity away, which means that the green jobs and the pink jobs and the yellow jobs are just not going to get any time on the workers to execute. So it means that, for example, your notification cleanup job is going to be running all right. Maybe there's going to be 2 of them running, but your email deliveries are going to stop. Your payment processing is going to stop, and all the workers are going to be taken by those blue items. And the solution to this is actually chopping a job that executes for a really long time into smaller pieces. And this allows you to schedule other jobs between your pieces. So imagine that here we delete notifications. Here we delete the first 10 notifications or the first 1,000 notifications, and we spool in the subsequent job, which deletes notifications starting from 1,001 up to and including 2,000, and so on and so forth. What this allows you to do, it allows you to create room or space for these jobs to execute as well. So it means that you are not allowing one job to gobble up all of your capacity. And also, as a good advantage, is that if you decide that you want to add more capacity and you have to start another worker, then it means that on that worker, again, those dark blue jobs, they are going to still be using a substantial amount of runtime, but also there will be some room for other jobs to execute. Whereas if you are in this scenario, very likely that if you start another worker or thread, this job is also going to start executing on that worker or thread. And then the worker that you just have launched when you scale up is going to immediately be completely consumed. And so we have a code for this, which is called Sequential Perform. And it's relatively straightforward. You add this module and you call this method in your active job class. and it says perform sequentially, and you tell it which positional argument in your perform method is an array of things, right? Very straightforward. So, for example, here we say that IDs of things are the argument 0, so the only argument to perform. And then we say, please do this in batches of 200. And then when you enqueue the subsequent chunk, enqueue it so that it spends between these many seconds on waiting on the queue before it gets delivered, so that we can create this window for other jobs to execute before the next chunk begins, right? And this gives the system a really nice property, is that your jobs also become interruptible. I think Kir has really done a lot of work on this.
Apart from chopping up jobs for the benefit of better scheduling, there is another reason you want your jobs to be as short as possible. And this reason is cloud environment. In the modern cloud, your workloads, your VMs, your containers can be terminated with a very little notice, let's say 30 seconds. And your job has to be able to interrupt within 30 seconds and push itself back to the queue. Otherwise, it would be the progress would be lost, which means that there is no way we can run a 2-hour job that iterates over a million of rows without having to interrupt it. When moving to cloud at Shopify, we spent quite a bit of time thinking about that, and also about the fair scheduling problem. And we came up with something called Iteration API. It's actually an open source gem, and you can try it if you're curious. But the gist of it is that rather than defining the job as a perform method, you define it as 2 methods. One method is a collection of things to work on. It's also a enumerator object. The API provides these easy helpers to build enumerator objects out of Active Directory relations, out of arrays, out of CSVs, anything you can imagine. And you can also put your own enumerator objects. And another part of job definition is the each iteration method, which describes what to do with every item of the collection. We found that this pattern of collection and action fits quite a lot of jobs on our platform. And right now, that's how most of jobs at Shopify are defined. And feel free to check out the gem and try it. It works with Sidekiq and Resque as well.
How long did it take for you to explain to everyone on the team how those enumerator builder method works, and what the cursor is and all this kind of stuff? Was it easy?
I guess we invest quite a bit into documentation and onboarding, but once developers are familiar with the pattern, they can navigate the code base fairly well.
This is commendable. This is commendable. And this one you also have some experience with, right?
Yeah. It's interesting to talk about something called congestion on resources. And we've all been in a situation where we see workers not catching up with the amount of jobs. Maybe it's a spike of traffic, or something is slowing down. And our first reaction is to throw more workers, throw more money into the problem. And sometimes that works, sometimes that doesn't. Let's go to the next slide. There is always some bottlenecks in the system. It can be a database. A database can do only given amount of writes per second. It can be a third-party API that always has some rate limits. And the more workers you have concurrently executing something in the system, the higher chance you will hit those bottlenecks. So it's not as simple as throwing more workers. And actually, we have to throttle things so that we don't do too many writes to the database, or we don't do too many third-party API calls.
Mm-hmm. That's a good one. That's this one, right?
Yeah. As I explained about iteration API, it wraps all units of work into these well-defined methods. And now that every unit of work is wrapped into something, we can do things platform-wide. So for instance, each iteration method from every job would be throttled based on the database health in a way that developers don't even need to learn about how to throttle on the database health, what signals to use, and so on, so on. And we can roll that for the entire fleet for all the jobs on the platform.
Oh, that's really sophisticated. We have it much simpler because, like, I would have never guessed that this thing actually throttles the DB, but I guess it's the trick it has up its sleeve. We do it in a more straightforward fashion. We just have a module called DB Waiter, and my former colleague Van der Hillen has made a great presentation about this technique at one of the Bang Bang cons, I believe. And what we do is on every batch that we want to process, we wrap it in a call to the dbwaiter.gently method, and this method is just going to wait for DB availability. So it's going to poll for a certain MySQL parameter, and it only is going to allow the method call to continue once this parameter is within limits. Yeah, I think this is much slicker, although I wouldn't have guessed what it does.
That's a lot of block of codes to wrap into dbwaiter gently.
Yeah, well, it is visible. It is visible, though. It is visible. Another thing that we encounter is Dockpiling. And by Dockpiling, I mean that at a certain moment, multiple jobs kind of paradrop down on one single resource, and then this resource gets overwhelmed. It can be the database, but for us, it can be external APIs primarily. For example, what happens when you shoot too many requests into S3 to a certain prefix, then S3 is going to give you back an error, which is called slowdown, which means that you are hammering it too much. But it will also, before it replies to you with this slowdown, it's going to hold up your HTTP API request for a long number of seconds, because they realize that if you have something in your system which sends them too many requests, then if they reply with a slowdown, you are likely to continue sending the requests at this rate. So what they do, they artificially stretch the response time to your request so that your system does not have the opportunity to continue generating more and more and more and more requests. And what happens then is that, imagine this job executes, the yellow one, and it executes okay because it has enough capacity on this specific API call. But then another job starts and it gets throttled. And it occupies this execution slot, and it takes, suddenly, instead of taking 300 milliseconds, it takes 30 seconds or 20 seconds before it finally fails. And in this situation, if you start more workers because you are not processing the jobs at a sufficient rate, what you're going to do, you're going to make the situation worse, because all of the jobs which try to execute the same API call, which is blocking or throttling you, all of these workers are now going to take 20 or 30 seconds, which means that all of the new workers that you start are going to be stuck waiting for this error reply from S3 in this particular case. So what we do is we apply a so-called concurrent execution lock in this situation. And the concurrent execution lock is something that sits between the job execution and the external resource. And what's going to happen is that here we execute a job which deletes from this prefix. So the transfer /AB can be one of the job arguments, for example, one of the job parameters. And if a second job arrives, which processes the same prefix and which wants to do the same call, what's going to happen is that before it's allowed to start, it's going to be canceled. It's going to be canceled and it's going to be thrown back into the queue with a certain delay, so that when it arrives in one of the workers again, the previous job, which consumes capacity on that shared resource, has finished. Meaning that we do not start getting into a situation where we get throttled, and we also free this slot so that this green job can execute in there instead. And we have a small thing for that, which is just called limit concurrent executions. We try to design our jobs in such a way that the shapes of the arguments or the parameters of the jobs are sufficient to set up this concurrent execution lock for that job, and this log gets applied before the job even starts. And for that, we use something called SUO, which is a very nice gem for implementing logs and token logs based on Redis or Memcached. And we use Redis as a supplement to SQS. So transient data, or the data we need very, very, very randomly, we store in Redis, but the jobs themselves has to be durable, and they are on SQS. And then, of course, you need to control this thing somehow, right, Kir?
Right. We also use a very similar way to control concurrency based on Redis as a metadata store. But what I wanted to talk about here is disaster scenarios and how we protect from those. Imagine an error in code that causes a certain job to get enqueued in the infinite loop, making the queue size grow through the roof.
Yeah,
or imagine something retrying indefinitely. We want a way to cancel all those things as an emergency tool to have control over the system. And ideally, we want to cancel those selectively. We employ ChatOps a lot at Shopify for all sorts of commands to manage and operate our infrastructure. And we also use ChatOps for jobs operation. And one tool called Blackhole allows us to send all the jobs of the certain filter basically to nowhere. They would not get executed at all. For instance, you could target a certain job class with any arguments, or you can target a job class of payment job with a specific tenant ID that equals a specific number. Or you could even use regular expressions if that's something that you want to manage based on params.
That's really nice. Also very sophisticated. I think we are a little bit more retrograde in this respect. We just have this, which basically you can set a key in Redis to discard jobs of a certain class, and you have to set that Redis key explicitly on the Redis cluster, and you have to set it manually. ChatOps are really nice, really nice, really nice. Would love to have this.
I would get slightly uncomfortable having to get into the live Redis on production to set up that force discard key, but I guess that works too.
Yeah, works for us, but I agree with you. It's uncomfortable. It is in time of need, man. In time of need. And we have the Classica.
Job priorities, something that every library offers as the first thing in the README, but also a topic that I don't think we talk enough about in the community. So if you start using Sidekiq or Resque or any other library, it will tell you to define a number of queues, and every job would have a queue assigned, and you can give a bit more workers to a certain queue or a bit less workers to another queue. Some queues would be higher priority, some would be lower priority, and so on and so on. If we look at e-commerce and like what are the actual business models that happen there, the one that's most important is the checkout flow. You go add something to the cart, proceed to the checkout, enter your mailing address, shipping address, and you want to see how much it costs to get something shipped for you. Checking shipping rates for a bunch of providers can take a long time. We don't want to do that from a web request, so that happens from a background job while the client is waiting. So we want the job to execute as fast as possible. That job would be in some of the highest queues. Then there would be payment happening at the step when you've agreed to that shipping rate and entered your credit card number and so on. And payment would probably take much longer because the process of moving money from one account to another account, pre-authorizing and doing all the checks with the credit card takes time. So maybe that would have slightly different priority from the shipping rate. And then there is different steps like updating the inventory, sending mail notifications, maybe sending webhooks to integrations about the fact that there is a new purchase. Some of those would have much lower priority of their queue than shipping payment rates or doing or processing the payment. So we employ queues quite a lot. And while it's not always very easy to choose the right queue, that's something that we wouldn't be able to live without from the operational point of view.
Okay, so this is somewhere I just need to throw this out there. I think priorities are no good for two reasons. So first, for us, those priorities are very hard to realize. We'll talk about this in a second. But also, the idea behind using priorities is usually that you say one job is more important than the other. So when there is not enough capacity to process all the jobs at the same time, let's process a certain job which has a higher priority, let's process it first. So you're making an operational decision upfront, as it were. You're making a guess effectively, and you're saying this job is more important, so let's let it execute first. What it gets you to is a situation like this. So imagine we're running a blue job, and the blue job has the highest priority. And as we in computer graphics, we used to say, I do not always set my render priority, but when I do, it's 99999. And so this blue job executes first, and it starts executing first, but it also has an error, and it also times out, and it's also slow on the database. So what it does, it consumes your entire worker thread again. So you've taken a unit of capacity out. It runs for a really long time. It does not allow other jobs to execute, and it effectively executes the guess that you have made that this job can start first. Whereas in practice, it will still cause the same operational concerns. And the problem with this guessing is that the actual priorities. Like most of the time, we find ourselves thinking about, it would be nice if this job had a lower priority than others, or we think, it would be nice that this job had a higher priority than others. Happens when we have an outage, and then we see, this particular job has failure, so it would be nice if it had lower priorities. But the failures can be intermittent. So a job that was perfectly fine yesterday and was talking to the same email provider, today the email provider's API is playing up, and so this job is suddenly causing you a lot of trouble. But the priorities you set in code, and you set those priorities in a structured manner in a commit. So it's not a knob that you can turn in real time. It's really a hard upfront guesstimate that you're taking and a bet that you're making. And also for us, it's way less relevant because it's SQS, and SQS does not have routing topics, which would allow you to have separate subqueues. Creating an SQS queue takes a lot of time because they use some replication things so that this queue is durable and reliable. And you only can create up to that many queues per account. So when you're creating a queue, you have to be you have to take that into consideration, how many queues you create. And those queues, they are really much more like heaps. They are not like Kafka topics. Kafka topics, for example, they are ordered, and they are not like routing keys in RabbitMQ, for example. So maybe we could have used priorities if we were using a more sophisticated message broker, because those systems like Sidekiq and RabbitMQ and SQS, usually they're called message brokers. But for us at this time, using priorities would actually create more trouble than it's worth, I think. For us, we take the easy and the easy hard way out is that we try to get into a situation where, on average, more or less, most of the jobs fit into a hard known time window. And if the jobs start exceeding this time window, then we take operational measures based on that, as opposed to making bets as to, if that job was scheduled first, then maybe our performance would have been better than if it weren't. But like I said, that's our approach. That's I guess that whole theme of different approaches, it kind of resonates here, right?
Yeah, I think it's time to wrap up. And it's interesting to note that like Shopify and WeTransfer have slightly different number of developers. At Shopify, we have hundreds of developers working on the same monolith, and we optimize for different things and different styles of APIs. And it's interesting how, based on this talk and different examples, you can see how different number of developers leads to different solutions. But at the same time, a lot of things are very similar. Like operational concerns are very similar. Both everyone needs fuses, early cancellation, concurrency controls. Everyone needs the safe deployment strategy with two-step deploy to avoid losing jobs. Everyone needs scalable and durable data storage for jobs. Either it's Redis that you manage yourself, or Redis that your hosting manages for you. Either that's SQS, and all the knobs and real-time controls. We both need them.
Yeah, and I think this is actually something that a lot of those message brokers could learn from Sidekiq, is that the Sidekiq was kind of pioneering in that regard, and that they ship an application which you can use to manipulate your job queues out of the box. You just have to install it into your application. But we can see this becoming more and more of a subject in the coming years or months. Like real time controlling your loads and the settings of your job execution in real time is certainly going to be something that's going to become more popular. And you don't need all of the above that we've just listed, right, Kir?
Yeah, we don't want the audience to get overwhelmed of oh, this is so many tools that I now need to develop and adopt. You don't need all of this, but you might need some of this. And don't think that we just all figured it out. Every tool that we mentioned today came out of an incident or some kind of terrible thing that happened in one of our apps that led us to come up with some safety mechanisms to protect from it. So it's years and years of learning from our mistakes. So hopefully you can use our talk today as a cheat sheet, learn from our mistakes, and do some exciting stuff with background jobs.
Yes. And now, by means of amazing video technology, we're going to jump back into real-time space with you, and we're going to be happy to take any questions.
Thanks everyone for listening.
Thanks, everyone.
Hi there. Thank you so much to the both of you. That was absolutely wonderful. So we are coming on pretty close to the time slot for our panel discussion. So I don't know. Do we have time for a quick question, Raita?
I think we're gonna go straight to the panel.